So like I said, now we've gone from 6 sides. We've increased this thing. If you look and you count the number of sides all the way around this thing, we've got a lot more sides. We've got 10 sides. And of course the area changed a little bit. You can think about how the area would change if you add a bunch of sides on there. We're still going to do the same thing. Still trying to get this area, this yellow shaded area, in terms of the radius of the circle or the radius of the actual polygon. So the process is the same. You've got 10 sides now. To find this angle, of course, you do 360 divided by 10, which would tell you that the central angle is 36. If I sketch in an apothem again, the apothem cuts that in half, which means each of these tiny little angles on your paper are 18 degrees. Should make sense. You've done that a few times throughout this chapter. Now is where we bring in the trig. I want to get the same thing you did before. I want to get the apothem in terms of the radius, almost exactly like the last one. The apothem is adjacent. The radius is the hypotenuse. You're doing a cosine ratio again. This might be a good time to pause and try to do the rest of this on your own. It's the same process we just did with the hexagon. Now we're doing it with the decagon. Some of the numbers are a little different, and the computation is a little different. This is the same step here. Multiply both sides by r, and you get r cosine 18. Again, you might want to pause, work ahead if you want. If not, here we go. Same idea I did before. I'm going to call this little thing x for a minute. Think about how many of these x's gets me around the entire perimeter of the polygon. Of course, there's 2 of them here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 of them get me around the entire thing. The perimeter of this thing is 20 times whatever x is. Now I want to get x in terms of the radius. So I need some trig to get me there. Same as before, the x is across from or opposite the 18, and the r is still the hypotenuse. So if you're thinking opposite over hypotenuse, of course that's a sine ratio. So sine of 18 is x over r. Same process as before. Solve this thing for x. In other words, multiply both sides by r. So r times sine 18. On the other side, the r's would cancel, and you'd have just x left over. You're now ready, like we were before, you're ready to take this equation and get this thing all in terms of r. So the apothem we replace with r cosine 18. The perimeter we replace with 20 times whatever x is. 20 times r sine 18. And you'll at this point you'll start to see some trends on here, some similarities with the last one we did. R times r, just like it was in the last one, is r squared. We still have cosine 18 and sine 18 that we can't do anything with other than crunch on a calculator. Half times 20, of course, is 10. So it's kind of interesting. For the hexagon, this was 6. For a decagon, this is 10. If this was a pentagon, you'd probably go, oh, that's going to be 5. If this was a dodecagon, that would be 12. If this was a triangle in here, this would actually be 3. Kind of makes sense. And of course, the 18, comes from this process here of dividing it by 3, dividing the number of sides by 360, and then cutting that in half. So take a minute, crunch this on your calculator, do 10 times whatever that decimal is, times whatever that decimal is. You get something different than the last time. Last time I think it was like 2.5. It's a little bigger this time. 2.94 is what I got. Double check me on that. I think I'm correct down there. And think about that. That kind of makes sense. If you look at the picture on here, the yellow space is maybe look at it. Think about it. Is it filling more or less of the circle than the hexagon? And that it sort of confirms that this is a little higher than the last one, 2.94 r squared. So at this point, some of you might see where I'm going with this, might see why I'm having you do this. If you look at 2.94, you've seen something like that before. 2.94 times r squared is equal to area. Think about that for a second. I'm going to jump to the next phase of this, which is the bottom of your paper. I'm going to just recall both of those equations we just came up with. This is the hexagon, you just did this. And this is the decagon, you just did that one. We had 2.59, then we got to 2.94. You might be able to tell what this decimal, what this approximate value is approaching, if you think of what we're actually doing on here. So to really go extreme on this thing, try the exact same process with a 20-gon and a 180-gon. In other words, something with 20 sides and something really dramatic, 180 sides. I'm doing this on purpose. I'm trying to get to the dramatic situation where the number of sides is like huge. really impractical, something you certainly wouldn't want to draw. But do the same thing. Find these calculations. Find something like this, 2.59r squared for a 20-gon, and find it for an 180-gon. And you can kind of see the trends on here. For a 20-gon, this is going to be 20. Think about how you got that angle. You took the 360 divided by 20. Of course, that would give you 18. This is a good spot to pause and kind of work these two on your own. And by the time you get through this one, you'll kind of know what formula we're deriving out of all this. Again, the 18 wouldn't go up here. Of course, it didn't go right there. Remember what you have to do with the 18 when you draw the apothem that cuts that in half? And you get something like this. Area is equal to 20, because it's a 20-gon again. Cosine of 9, because it was cutting this in half. Sine of 9, these both appear in this again. If you multiply these two decimals and multiply them by 20, I think you get around 3.09. I still haven't told you what you're deriving here. I'm hoping you see it by now. 3.09r squared. Really close to something else that you've seen in math. Try it with 180-gon. Same deal. Figure out this central angle. So you do 360 over 180. Really, really small angle now because there's so many sides. That central angle is only 2 degrees. Again, the apothem cuts that in half. So the area of a 180-gon would be 180, the number of sides, times r squared, times the cosine of 1 and the sine of 1. And you might think if you make this sides really, really, really big, the area is going to get like infinitely large. It's going to be huge. The area is never going to stop. Well, there is certainly a limitation on how big the area can get. Think about if you were to, this is a balloon in here, and you expand that balloon. What's the biggest this yellow balloon could possibly get? And hopefully you're thinking it becomes a circle. And maybe this connects all the ideas together here. Where have you seen that relative to a circle? Well, of course, that's pi r squared. That's what we're essentially deriving the equation for the area of a circle. That's what we've just done in a sort of 4 calculations here. We've taken the number of sides in a polygon and we've gone bigger and bigger and bigger, so big that it actually is 3.14. And if we looked at your calculator and you kept more decimals, and maybe you made this a 360-gon, you'd get even closer and closer and closer to the value of pi. Flip the page. I think there's one question on the bottom of your page. Maybe read that over to yourself and answer that. Maybe go back up to the top and write down what you've actually just derived on here. You should kind of have a good idea of it. I'm going to stop and go to part 3 here.